Hey everybody, welcome to Pre-Calculus Unit 1, Function Analysis. Piecewise functions. This is the final type of function we're going to talk about. And we've learned so much about functions at this point that anything that we've talked about with functions is, again, fair game with this new type of function called a piecewise function. All right, so first off, what is a piecewise function? The piecewise function is a function made up of two or more functions that are, well, pieced together, hence why they're called piecewise functions. Each piece has an inequality attached to it to know when to use that piece. So what piece of the function do you use is all based on the x value. So here's an example of a piecewise function. We usually see the f of x written. It's pretty standard. And then what we see is the, this bracket, curly bracket here. And inside that curly bracket are the different pieces. So this function has two pieces, x plus 2 and 2x squared minus 4x plus 5. So it's got a linear line and it's got a quadratic, which would be a parabola. Now, when do you use which piece of the function? Well, that's what the inequalities tell you. So here, if x is any value less than -1, you use this first piece. So if x were to, say, be -7, you would use this first piece. -7 plus 2 is -5. Therefore, the function is -5 when x equals -7. If x is any value greater than or equal to -1, then you're going to use this second piece, the quadratic piece of the function. So if x is, say, 15, clearly greater than or equal to -1, you would plug 15 in the bottom function and get out your output. Now, these types of graphs make really cool graphs, or these types of functions make really cool graphs. So let's take a look at the function that we just were showing you as a graph. So notice that at -1, we see a change. So you don't have to, but you notice that you can put a dotted 1 here. I'm not putting a dotted line here as an asymptote. I'm just trying to show you that right here, where x equals -1, we see the cutoff, right? Below -1, when x is less than -1, we see our linear line. This is the line x plus 2. Hopefully you're very familiar with lines, okay? But when x is greater than or equal to -1, we see the beautiful parabola that we see here, the 2x squared minus 4x plus 5. So this is a great picture that we see here of this piecewise function. Very, very nice. So from the graph, I could say, well, what happens when f equals 2? Now, algebraically, I could just plug that in to the second piece, because x equals 2. Or I could just look at the graph and say, oh, when x is 2, it looks like I have a point at 5. Okay? I could ask about when are you increasing, when are you decreasing, all that fun stuff that we've already talked about. We can notice that, hey, right here at 1, 3 is a relative min, or a local minimum. I change from decreasing to increasing. That is a sign of a relative minimum there. All right, now there's a little extra bonus question here. I wouldn't say bonus, but an extra question here that's really important to talk about is the function continuous at -1? Now, we've spent a lot of time in previous videos talking about what it means to be continuous, but we've got to check three things. So if we look at -1 here, we say, what's happening as I approach -1 from the left? And from the left-hand side, it looks like I'm approaching +1. What happens as I approach -1 from the right-hand side? As I approach from the right-hand side, it looks like I'm way up here at 11. Clearly, they're not coming together. That's going to be a big issue. So the first obvious answer is no, I'm not continuous at -1. But also, what happens at -1? Well, with the graphs like this, it's kind of a little bit trickier to see. But, am I allowed to equal -1? Well, yes, it does say on the bottom piece that if x is greater than or equal to -1 to use that piece. So at -1, if I plug -1 in, I do plug it into the bottom piece, and I do get 11. So there is a dot. There is a solid dot here. So there is a point there. So -1 is in the domain because I'm allowed to plug -1 in, but I'm not continuous with -1 because the two sides aren't matching up. So if you think about it, 3 of the continuous conditions are met. The right side is at 11. The function is at 11. There is a point at 11, but the issue is the left side is way down at 1, creating that jump discontinuity. And these types of discontinuities often do occur because when you're piecing different functions together, if the pieces don't all mesh directly together, then you're obviously going to have discontinuities. All right, let's take a look at a way more advanced piecewise function here. This is made up of 4 different pieces. 4 different pieces. So the first piece is what happens if x is less than -1. So any value less than -1 is going to use this first piece. If x is any value between -1 and 1, we're going to use this second piece. If x is between 1 and 2, we're going to use this third piece, which is a square root function. And then if x is anything greater than or equal to 2, we're going to use this fourth and final piece. So kind of complicated, but here's a picture, and it's really nicely color-coded. So you could see the red part, the blue part, the green part, and then the purple part is the fourth and final piece there. So it's pretty nice, pretty cool. So we see a lot of, interesting things happen, right? For example, we see a discontinuity at -1. Now, -1, understand a couple things as to why there's a discontinuity at -1. A, I can clearly see an infinite discontinuity. The right side of -1 is going up forever. The left side is going down forever. That's an infinite discontinuity. But check this out. I'm actually not even allowed to plug -1 into this function. It's not even possible because the first piece says if x is less than -1. The second piece says if x is between -1 and 1 or equal to 1. So there's no or equal to sign right here. So I'm not even allowed to plug -1 in, even if I wanted to. Not allowed. Can't do it. We also see another discontinuity at 2. So if x equals 2, I do use the bottom equation, which does produce a point right here at 2, 4. So there is a point at 2. That's a good thing. The right side is approaching that point, going towards 4. But check out the left side. The left side is somewhere down here. Looks like it's approaching 3. So again, a discontinuity. The 3 conditions don't all match up. 2 of them do, but not the third one. Sorry, discontinuous. But I also want to make note of +1. +1 is another place where the pieces come together, but we are continuous at +1. So check this out. First off, there is a point at +1, 1, 2. You are allowed to plug 1 into this second function because this second function says if x is between -1 and 1 or equal to 1. So I'm allowed to plug 1 in to this second function, and you do get 2. You get 8 on top, 4 on the bottom. 8 divided by 4 is 2. And you can clearly see a dot at 1, 2. But check this out. The left-hand side is coming towards 2, and the right-hand side is coming towards 2. So because I am continuous there, the 3 conditions are met, there is, I guess I would say I am continuous at 1, whereas at -1 and 2, I was discontinuous. So that's an important thing that we could talk about with these piecewise functions. So this is a pretty complicated one, but also a pretty cool function that allows us to piece 4 different graphs together and talk about them. All right, so let's continue talking about this idea of continuous or not continuous. So I hope you realize based on this graph, we do see 3 issues, but only 2 of them are discontinuous. So at 1, the 2 functions come together, but they're coming together and they're meeting at a point. So the left side, the right side, and at 1 are all coming together, which is beauty, which is continuous, right? So a very common question that we get with these types of problems is, how could we force 2 piecewise functions to meet and become continuous? So this is a great, really good, pretty advanced question for an honors class. It says, find the values of k that make the function continuous. So we have this piecewise function here, but we don't know what k is. K is missing. Obviously, x is missing, but x is a variable. X is always missing, right? Every function has an x in it. Well, not every function, but most functions have an x in it. That's the whole point of it being a function. So there's a lot that we do know in this problem. I use the top function if x is greater than or equal to -4. I use the bottom function if x is less than -4. But the question is if these 2 pieces are going to come together, who knows what they look like? The top one's a quadratic, the bottom one's a linear line. But if essentially we got a left piece and we got a right piece, and if they are going to come together, the left side and the right side have to come together at the same point. That's what it means to be continuous. They're coming together. Okay, so I got to figure out how can I make this happen? Well, think about it. All I need to know is that -4 is where this potential coming together needs to happen, because that's the x value where the function splits. Left side, I use the top piece. Right side of -4, I use the bottom piece. So -4, actually I said that backwards, the top is greater. So I use the top function for the right side, the bottom function for the left side. Okay, it doesn't matter. The point is that when x equals -4 is where this joining comes together. But I need them to join together. I need them to be equal. So essentially, I want k squared plus 80x to equal kx. If the two pieces are equal, then it's going to be continuous. Now, where do I want them to be equal? -4, because -4 is where I stop one function and start the other. So I'm going to plug -4 in for x. And what I have to do now is simply solve for k. So I get k squared minus, if you need a calculator, I mean, hopefully you don't need to, but you never know. 80 times -4 is minus 320 equals -4k. Now what I need to do is, it's a quadratic. Oh my goodness, we've spent a lot of time solving quadratics. So I'm going to leave the k squared. I'm going to add the 4k over, and I'm going to subtract the 320 still, or I'm just going to leave it as a minus 320, and I need to solve this. How do I solve this? I could factor, complete the square, or I could go ahead and use the quadratic formula. Now, this looks like it might scare you, but believe it or not, even with that huge, enormous 320, this is factorable. It might not be something that you would readily recognize, but it is, again, very factorable. We have k times k is the only way to split apart a k squared. Now, 320 has several factors, but it might take you a while to figure it out, but 20 and 16 are two factors of 320. And if I make it a positive 20 and a negative 16, when I subtract them, I will get the positive 4k in the middle. How cool is that? So k, now remember, if you were like, there's no way I could factor that on my own, use the quadratic formula. Complete the square. Actually, completing the square would be pretty easy on this one. And you'll still get the same two answers as I'm about to get. So using the zero product property, k could be -20, or k could be positive 16. So there are the two possible values for k. If I were to turn these k's into either, both of them would have to be the same, right? If I make them both 16s, I will create a piecewise function that meets, is continuous when x equals -4. Or if I turn both of those k's into a -20, I will create a piecewise function where they both meet, both sides meet, and they're therefore continuous at -4. So pretty cool, pretty easy example, and hopefully I took some time there to really have that make sense. All right, now, what are the many different things I could ask you to do with a piecewise function? Well, one of them is I could just ask you to evaluate a piecewise function using a graph. So I'm going to show you a picture of the graph, and I'm just going to ask you to evaluate a couple things. So what happens when what happens to the function when x equals 1, f of 1? So it looks like when x equals 1, I see a clear dot at 2. So the function is 2. Now, what happens to the function when x equals 2? Now, I know it's kind of hard with the program I use to make the graphs, but it's pretty obvious that there is a definite dot at 4, and there's no dot here. I can't really make open circles with this program that I made this on, but the fact there's no clear, solid, filled-in dot there is done on purpose. There's clearly a hole right here at 2, 3. So at 2, I'm actually at 4. There's clearly a point at 2, 4. All right, what about -3? And, sometimes we just have to use our best guess, especially if we don't have the actual function in front of us. But at -3, it appears that we are, I don't know, I'm going to take a guess and say 2.8. Again, you just kind of have to eyeball it sometimes. No big deal. What about at 0? At 0, we're looking at the y-intercept, and it does look pretty close to 2.5. I might be off a little bit, but that's a pretty good guess there. And finally, what about -1? Well, if I'm looking at this, -1, I mean, nothing happens. It's an asymptote. It's a vertical asymptote. It's not continuous, so nothing is there. DNE, there's nothing happening at -1. So you can evaluate piecewise functions with a graph quite easily. All right, we could also do it without a graph. So here's actually the function that we just saw, but let's pretend we don't have the graph. If you just have the equations in front of you, you could likewise evaluate the piecewise function. So for example, if I say, hey, what happens when x equals 2? What's f of 2? Well, first you got to plug it into the correct piece. So if x equals 2, I'm going to use the bottom equation here because this bottom equation says x greater than or equal to 2. So I'm going to do 2 plus 2 over 2 minus 1 squared. And you could probably do a lot of this work in your head, but I got 2 plus 2 minus 1 is 1. 1 squared is 1. 2 divided by 1 is 2. So 2 plus 2 is 4. So there's my point at 2, 4. All right, what happens when what happens to the function at -1? So again, where do I plug -1 in? And then you realize I can't. The top function is only if you're less than -1. The second function is only if you're between -1 but not equal to -1. So that is why that is a DNE, which remember, we saw that in the graph that we just looked at as well. What about when x equals 5? Well, once again, 5 is greater than 2, so we're going to once again use this bottom equation. So 2 plus 2 over 5 minus 1 squared. And then walk yourselves through it. So let's see here. 5 minus 1 is 4. 4 squared is 16. 2 sixteenths is 1/8. And 2 is 16/8. So 16/8, which is equivalent to 2, plus 1/8 is 17/8. So there's my answer. It's 17/8. And one more to go here. What happens if x is -4? Well, in this case, I'm going to go ahead and use the top equation because -4 is less than -1. So I get 3 minus 1 over, let's see here, -4 plus 1 squared. And that's 3 minus -4 plus 1 is -3. -3 squared is 9, so I got 3 minus 1/9. 3 is 27/9. 27/9 is equivalent to 3 with the common denominator. So 27/9 minus 1/9 is 26/9 for a final answer there. Pretty cool, pretty easy to do. Make sure that that makes a lot of sense to you guys. Now, if we look at the graph, we already know that at 2, I'm not continuous. There is a jump discontinuity. But what if we come back here and say, hey, prove to me that there's a jump discontinuity at 2. Well, you got to prove 3 things. The first thing I got to prove is that at 2, there is a point. So I use the bottom function if x equals 2, and we already know the answer to that from up here. There is a clear point at 2, 4. So the first condition is checked. There is a point there. But then I got to check both sides of 2. So what happens if I plug 2 into the left side? Now, this is the left side. Remember, the graph is making a switch at 2. It's going to switch from this piece to this piece. So I got to check both sides, right? So I got to check the left side, which would be plugging it in, even though I'm not really supposed to plug 2 into that function, right? That's not the piece I use. To check for discontinuities or continuity, I got to plug it into that left-hand side. So I'm going to go ahead and plug 2 in, and 2 minus 2 inside the square root, or 2 minus 1 inside the square root, plus 2, and the square root of 2 minus 1 is 1. 2 minus 1 is 1. Square root of 1 is 1. 1 plus 2 is 3. So I can clearly tell that this is not continuous because there's a point at 2, 4, but the left side is down at 3. So that, I'm just going to stop right there. I'm obviously not continuous, and the graph is really easy to see this. In the graph, I clearly see the left side is going to 3, whereas the point itself is actually at 4. So that's an instant sign that we're not going to be continuous. All right, being able to graph a piecewise function is also an important thing that you need to be able to do. So this can be very simple if your piecewise function is made up of linear lines, like we all know how to graph a line, come on. Or it could be very difficult if it's made up of more advanced functions like absolute values, quadratics, cubics, or some weird rational function. So let's take a look at this first example that is pretty much all linear, makes our lives very easy. So this is a really basic, nice and simple piecewise function. So the first piece is 2x plus 3, and this is actually cool. This is something we haven't seen so far. We use 2x plus 3, which is just a line, anytime x is not equal to 3. So as long as x does not equal 3, we use this first piece. So that's going to be pretty easy to graph. If x is 3, we're going to use -2. So if x is 3, I'm simply -2. There's not even an x to plug in for. I'm just -2. So that tells me that when x equals 3, there is a point at -2. So I'm actually going to go ahead and fill that point in right now. There is definitely a point at 3, -2. Now, for all other points other than 3, I'm supposed to simply use this function. You guys should know how to graph a line. Start at the y-intercept of 3, follow the slope, up 2, right 1, up 2, right 1, up 2, right 1, down 2, left 1, down 2, left 1, and then make a line. Pretty easy, right? Pretty simple. Hopefully your lines are a lot straighter than mine. But be careful. Remember, I need to remove the point that was at 3. Remember, I was not allowed to plug 3 into this top equation. This top equation was only for values not 3. So if x is 3, I was supposed to use this point, which is why I drew a point there at 3, negative 2. So what I'm going to actually do is plug in 3. Even though I'm not allowed to plug in 3, I'm still going to plug it in just to see where I need to put a hole. So 2 times 3 is 6. 6 plus 3 is 9. So right here should be an open hole. So you could grab an eraser and erase it if need be, or just kind of put a big hole there. But there's clearly a hole there because remember, I'm not allowed to plug 3 into this top function or this top piece. I'm only allowed to use negative 2 if x is 3, which made that nice simple point right there. So that's how you would do that. All right, so here is a little bit more complicated one where if x is any value less than 2, I'm going to use a line, which is pretty nice and simple. If x is any value greater than 2, I'm going to use this parabola. So the first thing I'm going to do is, you don't have to do this, but I actually kind of like to do this. Maybe do it with a light marker or a light pen or a light pencil. Is at 2, I'm clearly going to make a switch. So I'm not drawing an asymptote, please. I'm just trying to note that when x equals 2 is where I'm going to flip-flop. So on the left-hand side, I need to use the top graph. On the right-hand side, I need to use the bottom function or the bottom piece. All right, so this is just a point. Points are really, this is just a line. I'm sorry. Very easy line. So here is the y-intercept of 2, follow the slope, up 3, right 2. Now I'm going to have to put a hole there because I just realized that I'm never allowed to use 2. Check this out. The function never says to use 2. I could go less than 2, greater than 2, but I'm literally not allowed to use 2. Just can't use it. So I'm going to make sure there's a hole there too for sure. Down 3, left 2, down 3, left 2, and then you could make a line. So anywhere to the left of 2, I'm going to have this beautiful line like so. Now, if you don't like graphing lines in the way that I just did, you could just create points. I mean, plug in -5, get a point, graph it. And how many points you need to make a line? 2. So plug in -1, graph the point, connect the 2 points, and you got yourselves a line. Really not that hard. All right, then if I'm greater than 2, I need to use this parabola, okay? So, first thing is, I know that I'm not allowed to use 2. I'm not. But sometimes it helps get the starting point going, right? Because there's just going to be a hole there. So let's plug 2 in, even though I'm not allowed. I'm still going to plug it in. So 2 minus 3 squared plus 4. 2 minus 3 is -1. -1 squared is 1. 1 plus 4 is 5. So once again, at 2, 5 is another open hole. Why is there a hole there? I'm not allowed to equal it, right? And then from there, it's going to be a parabola. Now, how do you graph a parabola? I'm going to give you 2 ways to do it. One, just graph a couple points. So let's plug in, again, any value greater than 2. So let's plug in 3. 3 minus 3 is 0. 0 squared is 0. 0 plus 4 is 4. So 3, 4 is a point. Let's plug in 4. 4 minus 3 is 1. 1 squared is 1. 1 plus 4 is 5. So 4, 5 is a point. And let's plug in 5. Let's just do one more. 5 minus 3 is 2. 2 squared is 4. 4 plus 4 is 8. So at 5, 8. And again, this allows you to get a nice feel for the parabola. So notice there's a little bit of a curve. You got to make that curve. You guys know there's a curve in a parabola. The other thing you could do is remember our transformations. This is a parabola that went right 3, up 4. So if you think about the vertex, which is typically 0, 0, it went right 3, up 4. Hey, there's our vertex, and then you can make the parabola from there. But remember, the parabola does not continue past 2 because past 2, we switch and use this top piece. So there is a nice picture of that. All right, so the one issue, though, is graphing in Delta Math. Some of your problems are going to be in Delta Math, and you got to make a graph. Graphing's a little bit weird in Delta Math, so I quickly want to show you this real quick. Let's go ahead back to this problem and show you how you would make this graph in Delta Math, back to this linear line one. I'm not going to give you any more complicated problems in Delta Math. They'll be pretty simple ones. All right, so if I'm going to graph this function Delta Math, notice that Delta Math allows you to make a line, a closed circle, or an open circle. So I know that there is a closed circle at 3, -2, because the graph says if x is 3, I'm simply at -2. So when I go to Delta Math here, at 3, -2, I'm going to put a open, or not an open, sorry, filled in, why is it not letting me? A closed circle. I don't know why it wasn't letting me do it for a minute there. Now, notice if you hover over top of it, you get this X out sign. That's if you want to erase it. So if you want to go on, hover over top and click that. But again, 3, -2, there's a point. All right, now I need to make a line. And remember, you only need 2 points to make a line. So all you got to do is graph 2 points. So if you remember that my y-intercept is 3, then when you go here, obviously just put a dot at 3. Sorry. Oh, you got to cut a drag. So you got to click and drag. See, I'm learning as I go here too. So you got to cut it, click and drag, and then follow the directions of the slope. Remember, the slope was up to right 1. So when we come back in here, you're going to grab this and you're going to follow the directions of the slope. Now, again, I kind of messed up, right? So hover over top of it with the little X, red X, and it'll erase it. So I want a line starting at 3, followed up to right 1. And then you can keep going up to right 1. You can keep going up to right 1. If you want, down to left 1, whatever you want to do. But what I need to do is I need to turn this into a line, because right now it looks like a line segment. So once you have a couple segments drawn for your line, all you got to do is click, it'll make it open, click again, it'll make it a line. So once again, click once, it'll make it open. If it needs to be, click again, it'll make it a line. Now, the only other thing I need to do is remember there was an open circle, because at 3, 9 is an open circle, right? If x is 3, I need to use the bottom piece, which is -2. So when I plug 3 into the top, please emphasize, even though I'm not allowed to plug 3 into the top, I'm doing it to find out where that hole is at. I know that that's kind of weird to think about, but there's a hole there. I need to make sure I know where the hole's at. So even though I'm not allowed to plug it in there, I'm still going to do it anyway. So at 3, 9, there needs to be an open hole. So I'm going to click on open circle, and at 3, 9, I'm going to turn that into an open circle. Then you could hit turn in, submit this work. So that's kind of weird how it works, but the big thing is if you ever make it look like a segment, double click on the points to turn it into a line. So a little bit different there, but if you need to rewatch what I just did, go ahead and rewind. If you ever need to erase something, just scroll over top of it kind of, and when you see that, like, red X come up, click, and it'll erase. Okay? All right. Awesome. All right, so the other thing we need to be able to do is write a piecewise function from a graph. This is a little bit trickier, but I can show you a picture of a graph. You tell me what the piecewise function is. Now, what do we have to do here? How can we understand this? First, you have to be able to recognize a function. You need to be able to say, oh, that's quadratic. Oh, I see a curve. Oh, that's absolute value. I see a sharp turn. Oh, that's a line. You need to recognize functions. I hope we've learned that this unit so far. You also need to know how functions can be transformed. That way you can understand how they moved to where they are. And we also, come on, you better be able to know how to write a linear function. That's pretty easy. So here's an example where here's a function, and I want you to create a piecewise function that equals this. Now, I do see a couple different things I got to address. First off, the first piece is a line. I love lines. They're easy to work with. But this line is only from -4 to 1. And it's not including 1, because I noticed on this line there's an open circle there. So the first is only good, the first line segment is only good from -4 or equal to -4 or less than 1. So again, from -4 to 1, I'm going to use this line. Now I got to do is write the equation of that line. Well, come on, it's pretty easy. Looks like the y-intercept is at 1, and it looks like the slope is up 1, right 1, or down 1, left 1. So that is going to be 1x plus 1. Pretty easy line there to do. Come on. If you really don't like doing that, all you got to do is pick 2 points and go back to point slope form that we did in unit 0 and find the equation of the line between them. Not that difficult. Now, I also see that when x equals 1, there is a point at -1. So that's another piece. If x equals 1, there needs to be a filled-in dot simply at -1. So at 1, there's a dot at -1. So that's a piece. That is a piece to it. And then there's another piece for when x is strictly greater than 1. And I know that because there's an open dot right there. So if x is greater than 1, I'm going to use this last line. And that's a horizontal line. Horizontal lines are the easiest lines in the world to write. They're just numbers. So it looks like there is a horizontal line at -3. So at any value greater than 1, I am always -3. Any value at 1, when x equals 1, I'm a point, -1 right there. And then any value from -4 to 1, it looks like I'm using this line segment, x plus 1. All right, here's one more that we're going to take a look at, and this will be it for today. All right, so here is another piecewise function, and it does look like, for the most part, it's a line, right? So what is the equation of this line? Well, that actually is really, really easy, -x. The y-intercept is 0, and the slope clearly looks down 1, right 1, down 1, right 1. Slope is clearly -1, so -x. And it looks like I'm literally going to use that line everywhere except -5. So x does not equal -5. How do I know that? There's a clear hole at -5. I'm not allowed to plug -5 into this first function. But anywhere else, I'm good to go. Now, it does appear that if x is -5, I do need a solid filled-in point at a y value of -5, because there is clearly a point at -5, -5. So when x is -5, I need a dot at -5 as a y value. Everywhere else, I'm going to use the very simple linear function, -x, which produces the line there. So that's kind of similar to the problem that we did earlier as well. So hopefully that makes sense. Hopefully you guys don't mind piecewise functions. They are pretty easy. They're not overly difficult, but there is a lot to talk about, and we got to really make sure we know how to evaluate them, what they look like, what continuity means when you're working with the piecewise functions, and again, how to make a graph or create a function based on a graph. All right, sorry for the longer video, but there is a lot of detail with piecewise functions. Enjoy.